हेलो।
यस, बोलिए।
नहीं, we tried for DFS and BFS,
यस,
but got stuck to lot many points.
नॉट मेरी।
Lot many points जैसे स्टैक डिफाइन कैसे करना, स्टैक से लेना कैसे है, स्टैक में अगर अगर इफ रूट नॉट पॉसिबल तो एंट्री डिलीट कैसे करनी है, एंड लाइक दैट।
So these things actually we discussed in lecture 3, last lecture, right?
नो नो नो, नहीं, प्रोग्रामिंग स्टाइल में कैसे डिफाइन करना है, मैं वो सोच रहा था।
वो भी मैंने डिस्कस किया था लास्ट क्लास में।
हम्म,
When we talked about list, so आप लिस्ट को यूज कर सकते हैं एज अ स्टैक और अ क्यू, राइट?
नहीं, लिस्ट यूज किया, करेक्ट है। वी डिफाइंड इवन स्टार्ट पॉइंट, एंड पॉइंट, वी नो आवर गोल, हमें जस्ट पाथ फाइंड आउट करना है, दैट इज वी जस्ट नीड टू रीच द पाथ गोल। स्टार्ट किया 0 0 से, बट सी फ्रॉम लिटरल पर्सपेक्टिव वी कैन राइट, मतलब, बट जो पर्टिकुलर जैसे कि अभी सिस्टमैटिक वे जो है ना, दैट्स गेटिंग बिट डिफिकल्ट।
ठीक है, we can discuss after the class.
या या
Okay, so before we begin, I wanted to remind you कि we have I have already uploaded the assignment and the deadline is on Tuesday, not night, so it is on Tuesday afternoon, 12 p.m. So please submit before that time. And if you have any doubt, queries, you can just post it in the Google forum as well, that classroom forum. Okay. And these slides I have made today itself, and so there might be some errors in the slide. If you find some typo or here and there, you can just tell me, because yeah, I had just completed the slide 10 minutes prior to the class.
शुभ शुभ।
Yes.
One kind request to you, as the way you are sharing your video lectures, please also share these slides if possible.
I have shared the slides.
नहीं, हमें नहीं मिला स्लाइड।
I'll just show you, just a minute. Everything is there.
No, I could see the videos, but I
I,
couldn't see the.
I'll show you. I'll just show you. Just a minute. Everything is uploaded actually in the drive. If you go in my website, then you will be able to see. So if you search, visit this website, this is my own website, and go to resources. In the resources tab, you will see this course. So this is the course we are currently, so not just a minute, not this, click here. So when you click here, every video lectures are here, and I have given the access to lecture material over here. So if you click this, you will be taken to a drive where you will find.
Okay, okay, yeah, got it. Okay, okay, thank you.
All right. So we'll start today by, so in the last class we had completed the remaining portion of search and we were talking about state space search. We will move on to knowledge based representation and inference. So we will talk today about how a computer stores knowledge and how makes logical inferences. So the first quiz which I had given you was on logic, and you will see, so you have solved that problems in the quiz yourself. You will see how a AI agent will solve that problem by itself. All right. So you will see what is the structure of representing those informations and how an AI agent reason out what will be a logical solution to that problem which you have posed to an AI agent. All right. Yeah, so this is the flow of today's lecture. I don't think I'll be able to complete the whole today, but I'll try to cover as much as I can. All right. So let us see how a human represents knowledge. So knowledge refers to the collection of information, facts, skills, etc., or whatever experiences a human acquire throughout its life. All right. So there can be different types of knowledge. One can be declarative knowledge, which are kinds of facts, concepts, information which we absorb. All right. The other kind of knowledge is procedural knowledge. It is the skills which we acquire. So I am speaking in English. So this is a skill I have acquired throughout my lifetime, right? So this is procedural knowledge. And another is experiential knowledge. These are the insights gains from personal experiences and interactions. All right. So knowledge is contextual, dynamic, and influenced by emotion, culture, and social interaction. So the experience which I am having will not be the same as the experience which you are having. So both of us are having a different knowledge base and we are developing different kinds of skills as well. So procedural knowledge are also different. So I may not know how to drive a car, but you can drive a car. So we both have different kinds of knowledge. This enables reasoning. So this kind of knowledge helps us reason, helps us making decisions, solving problems, and so on and so forth. All right. So what is, how can we think about the same analogy in a computer? So knowledge refers to the structure and organized information that machines can process, analyze, and use to perform tasks. So we want the similar kind of knowledge so which humans have. We want to represent the same kind of knowledge in a computer. So what are the key characteristics of a knowledge in an artificial intelligence setting? So we have to have a representation. So if you remember in when we were talking about state space search, then we were talking about how to represent a state. Over here we are talking about how to represent the knowledge. What are the ways we will be able to represent a knowledge for a AI agent? How will that AI agent make an inference? All right. And then another key factor can be, you can specialize an AI agent to be a domain specific. So it can have a specialization in medical diagnosis, or it can have weather forecasting specialization, and so on and so forth. All right. So yeah, this is it. So this is one problem again I have taken. So this is similar to the quiz we had. So this problem has some statements and we will say that these are true statements which we are receiving. So this is the knowledge. Okay, so this is the knowledge and we want to infer something. These are the statements we have. So how a human will infer? So you can take 2 minutes to read the three statements which I have. And can you infer anything about this question? Take a minute and read. So it says the team will practice in the field only if and only if it did not snow. So this is a biconditional. All right. It works both ways. If it snows, then the team will practice, not practice outside or practice in the field. And if it didn't snow, then the team will practice in the field. It works in the other direction also. So if it didn't snow, then the team will play in the field, and if the team will play in the field, it implies that it didn't snow. All right. It is bidirectional. Another statement is the team practiced in the field or the team went to the gym, but not both. And another statement we have is we know that the team practiced in the gym. So what can you say about this? Did it snow today?
No.
Okay, so I heard a yes and a no. So can anybody tell me why did you speak as the solution as no?
The, the team practiced at the field, and the practice is possible only when it didn't snow.
The team practiced at the gym, not the field.
Okay, team practice. Okay, at the gym today. Then it didn't snow.
Then,
It
so
didn't snow.
if this is true, then this is not true because we know that both cannot be true at the same time. So if this is not true, therefore this is not true, which implies this is not true. All right, so it did snow today. Okay. So this is how we made a logical inference. So this is known as inference from some premise. So these are the statements which you are given. You are coming to a logical conclusion from this premise. Okay. Premise means, well, statements which you have. All right. And from this premise, you are coming to a conclusion. So what is the reasoning process? We discussed this. We went to the third statement first. We saw that they practiced in the gym today. Then we went back to statement 2 and we saw that if the team practiced in the gym, then they might not have practiced in the field because that is what the statement was implying. Now we went back to statement 1 and we saw that if the team did not practice in the field, that it must have snowed today. Therefore, the conclusion we have is it snowed today. All right. So this demonstrates how human utilize logic to draw conclusions and the reasoning from and reason about information. So our goal is to formalize this process in the field of AI. So we want an AI agent to have similar kind of conclusions with such informations. All right. So this is the goal which we have, and we want to learn how to do this. Okay. Any questions? So the first problem is how to represent knowledge in to a computer. So you might have known that computer only understands zeros and ones, and these are natural language. We are talking about English phrases. How will a computer understand these phrases? Which this is what the question talks about. What is a representation of knowledge? So how will we represent knowledge? We will see it later, but what is it is actually encoding information about the world in a formal structure. So in English, one word can have multiple meanings, right? So, but this is not true. This cannot be true for a AI agent. One word should have a specific meaning. So those things you have to take care of. That is why we are saying that in a formal, structured manner, such that the AI agent can use this information to make inferences, reasoning, and decision making. Okay, so what is the importance? So for example, you can have, so we have natural language processing softwares right now, right? So we can have a GPT software, you can talk to them. So those are also using some natural language processing information. They are storing that information and then making logical inferences and then communicating. All right. This can be critical in many applications. For example, in medical fields, you can submit some symptoms, some lab tests, and that will come to a conclusion that the patient has a disease or not. So there can be many applications for this. So there are many applications, but it is important to realize that a representation of knowledge is important to understand, and this will help us inform the AI about the facts which we have currently. All right. So what are different types of knowledge? There can be a declarative knowledge. So earlier also we talked about declarative knowledge are like facts of the world, which represents facts of the world, and procedural knowledge are like procedures or a step-by-step instruction of how to do a task. All right. So the process of diagnosing an illness from a set of symptoms. All right. So these are procedural knowledge. So the key takeaway is we want to make this kind of information available for an AI. How will we do that? Okay. So the first concept which we will use is propositional logic. There are other ways to represent knowledge and infer from the knowledge which we have. But first we will talk about the propositional logic. In propositional logic, this is the simplest form of logic where a statement which is actually a proposition can be either true or false. So for example, it rained today. This is a statement and we'll call this as proposition. And this statement can either have two values, true or false. All right. So such kind of statements are known as propositions. And the logic will apply to these propositions are known as propositional logic. All right. Atomic statements about the world, such as is it sunny? So this is also a statement. It can have two values, either true or false. Okay. So we can assign these kind of propositional statements a symbol. So we can say P is what? P is signifying it is sunny. So if I say P, the computer will understand that it is sunny. And if I say not P, a negation, not P, then it will mean that it is not sunny. All right. So this is how we can define propositional symbols, and it represents some idea in the real world. Okay. So when a computer says P is true, then we can infer whatever that P represents, we can say that that is true. Okay. And there can be logical connectives. So in propositional logic, you have to understand what is a propositional symbol. So a symbol is just a representation of some propositional statements, which can have either true or false. And there can be logical connectives. These connectives helps give information about the propositional symbol. So if I say not P, we can write it as like this. So this is a connective which is known as negation. So you are saying not P. So P is not true. Okay, P is false. We can have a conjunction P. It is like an A, but that middle sign is not there. It means and. So P and Q. Okay, conjunction. This is P V Q, which means or. P or Q. So what does P or Q means? Either P is true or Q is true, or both are true. P and Q, what does it mean? Both P and Q has to be true. Okay, or is true. Implication. Implication means if P is true, then Q is true. Okay, if P is true, then Q is true. And bidirectional. So in the first example which we had if and only if. Bidirectional implies if P is true, then Q is true. If Q is true, then P is true. If P is false, then Q is false. If Q is false, then P is false. If Q is true, then P is true. So all the implications will be there. Okay, so it is a bidirectional. So we'll see the truth table of all the 5 logical connectives, then it will be more clear for you. Okay, so a negation. So it is very simple to understand. It will just invert the value. If it is true, then it will become false. If it is false, then it will become true. Okay, so if P implies it is raining, not P will say it is not raining. Okay, so if P has a value of true, then it will become false. If P has a value of false, then it will become true. Conjunction is always, so this is the statement P conjunction Q, P and Q. This will only be true when both are true. This statement, this is also a statement. This statement will only be true when both of them are true. Okay, so when P is also true and Q is also true, then this statement P and Q will have the value true. Otherwise, it will be false. Disjunction. Disjunction means either P is true or Q is true. So you see here Q is true, then this is also true. When P is true, then this is also true. When both are true, then this is also true. So this is like English, this or this. But you should keep in mind, this is not exclusive or. So we are saying both can also work. So if both are true, then also it will be true. Okay. So this is a this is known as disjunction. We can have implication. So implication, you have to understand, it might be tricky for few. You see, implication, when I say if P then Q, so it talks about when P is true. When P is true, then this happens. It doesn't talk about what happens when P is false. It doesn't matter. So when P is true, then Q must be true. Okay. So if this implication is true, when P is true and Q is true. When P is false, I have no information about Q. So Q can take value F or T. Matlab F is false and T is true. So in all the three cases, this implication will be true. Only when P is true, only when P is true and Q is false, then this implication becomes false. So I'll just give you one, I'll just reiterate what this means. This implication says if P is true, then Q must be true. Okay. So whenever P is true, then Q must be true. You see, therefore this implication gives a true value. When P is true and Q becomes false, then this implication doesn't give a true value, because this cannot happen. When P is true, then Q cannot be false. Therefore, this implication is false. But when P is false, then we have no information about Q. In that case, this implication will hold true value, because it doesn't give any information about Q when P is false. Okay, so this is true for three cases and only false. So you should, from here, you should always take home from this is that if you have an implication, it will only be false when P is true and Q is false. Okay, and bidirectional, if both take the same value, then it will be true. If both take different values, then it will be false. So if P and Q both are false, then P bidirectional Q will be true. And for both are true also, it will take value true. Otherwise, it will take false. Any doubt? Any questions? Okay, so these are logical connectives in propositional logic. Okay, so I have taken some examples of implication and bidirectional because it might be tricky to understand. So it says that it is raining. So P is a propositional symbol, which means it is raining, and Q is a propositional symbol, which means it rain. The road is wet. All right. So this statement, it is raining. If it is raining, then the road will be wet. Okay. So if it is raining, then the road is wet. Okay. But you see, when this holds true, then this must be true. But when this is false, then you don't know the road is wet or not. Okay, so this is how implication means. Any questions? All right. A bidirectional, so the car engine is running and there is fuel. So it says that the car engine will only run if you have fuel in the tank. It also implies if you don't have fuel in the tank, the car engine will not run. On the other hand, also it will imply that if you don't have fuel, the car engine, so it means P bidirectional, Q can go this way also, this way also. Okay, and it also means not P bidirectional, not Q. So this way also and this way also. Okay, bidirectional means if both are false, then the bidirectional is true. If both are true, then the bidirectional is true. So we have a way to represent knowledge. We can represent statements, propositional statements as propositional statements, symbols, and we can relate two propositional symbols with a logical connective, and you can form complex statements and paragraphs using these propositional symbols and logical connectives. Okay, now we have a way to represent knowledge. Now we have to reason out how to make inferences from this knowledge. All right, so we know a way to represent knowledge. Now we have to understand ways to make inferences from that knowledge. So there are few more terminologies you have to understand. First, what is a model? So this is not the same model we were talking about when we said state space search has a model. So that is a search space model. All right, so this is a different kind of model. You can think about is as worlds. So suppose you have a statement, this statement. I'll just erase everything over here. It has two symbols, P and Q. Okay, so if I say P is taking true value and Q is taking true value, so this is a model. If you give the values to these symbols, then it becomes a model. You can have multiple models in another. So this is model one. In another model, you can have P as false and Q as true. Okay, so you can have multiple models. Over here, if you have two propositional symbols, then you will have 2 to the power 2 models, which is 4. So you can 2 values for P and 2 values for Q. If you have n propositional symbols, then the number of models which you will have is 2 to the power n. All right, because each of those propositional symbols can take either true or false, and you have n number of such symbols. So 2 into 2 into 2 into 2 till n. So it becomes 2 to the power n. Okay. So this is what a model is. A model assigns truth value, either true or false, to propositions or propositional statements. Okay. By providing these values, a model reflects our understanding of reality and convey information about various conditions or situations. Okay. When we are saying this statement is true, then we are conveying some information to the AI, not AI agent, in general. So if I tell you a propositional statement and I give the truth value of that propositional statement, I convey some information to you. So for example, if I say I am at the beach, which is C, and D is sunny. So one model can be C is true and D is false. It means I am at the beach and it is not sunny. Okay, so this is one model. You can have multiple models. You can say C is also false and D is also false. It implies that I am not at the beach and it is not sunny.
You are stuck, Shubham. Your video is paused.
Hello, am I audible?
Yes.
Yeah, now you are audible.
Yeah.
So yeah, sorry for that. Okay, so what did you last hear? So I was talking about how you can have different kinds of models for different propositional symbols, right? So was that clear?
So you were on the beach.
Yes, yes. So I was saying that these symbols can take different values and you can have different kinds of models, or you can think about different kind of worlds. So in a world, you may be at the beach and it is sunny. In another world, you may not be at the beach and it is sunny. In some other world, you may not at the beach and it is not sunny, and so on and so forth. Okay. So this is what a model is. And I have given here multiple examples of. Is it clear? Am I audible again or not?
Yes,
Yeah,
Okay.
intermittently.
Your voice broke for like 1 minute.
Oh, I'm sorry, I don't know what is happening. So yeah, so so I hope I have made you understand what a model is, right?
Yes, yes.
Yes.
Okay, okay, okay. So now we'll understand what is a knowledge base. So you see, we have models. Now you can have different kinds of collections of facts. So you can give me one fact, you can give me another fact, you can give me another fact, and the collection of all the facts combined is known as a knowledge base. Okay. So please respond, because I'll not be able to understand if I'm audible or not. Okay. So if I go back and come over here, you see I have multiple statements. I have multiple statements. If for these statements I make some models, so if I say this is A, this is B, this is C, and I give values to this. So A is true, B is true, and so on and so forth, right? And I combine all this and I give you. So this is what a knowledge base is, a collection of propositional statements in a world, in a model. Okay, so this is what a knowledge base is. Is it clear?
Yes.
A collection of known facts and rules often used to reason in AI system. Okay. Consistency. A knowledge base is consistent if there is at least one model where all statements in the knowledge base is true. So you see, you can give me some facts which combined may not be true. So that is not a consistent knowledge base. A consistent knowledge base is when I combine all the facts, there should be at least one world when the knowledge base becomes true. Okay, is it clear? Or how, should I explain this point once more? Okay, so I hope it is clear. So consistency just means if you're giving me some set of facts, it should be true in some of the worlds. It might not happen that it is not true in some of the world. It is not true in any of the world. Okay, so there is no contradiction. This idea of entailment is very important. What does entailment mean? So you see, I am saying this represents alpha entails beta. If I say alpha entails beta, it means that in every situation when alpha is true, then beta must be true. Okay, so it says that if I have a situation when alpha is true and I enumerate all possible situations when alpha is true, I should have that beta is also true in such situations. Then only I can say alpha entails beta. So why are we talking about entailment? You see, what we can do is I have a knowledge base, right? I have some information with me and I have a question. So for example, if I go back, whether it is raining today or not, I had some information and I can list down in which worlds this knowledge base is true. In all such worlds, when the knowledge base is true, this whether it is snowing or not should be true. If it is so, then I can say then this information, this knowledge base which we have can imply that beta is happening, beta is true. Okay, so from this I want to conclude then whenever alpha is true, beta is also true. So for example, if I have a knowledge base which is represented by this Venn diagram, so I'm saying this is my knowledge base, and if beta is this, then I can conclude whenever my knowledge base is true, then beta is true. So this is what entailment means. If I have a knowledge base like this and I have beta like this, then I cannot say my knowledge base entails beta. Over here I can say my knowledge base entails beta. Okay, so whenever my knowledge base is true, beta has to be true. Or in place of knowledge base, you can think about just alpha, because I'm writing alpha entails beta. So when alpha entails beta, this is the situation. Whenever my alpha is true, beta is true. Is it all right? So
Yes, sir.
you can relate this idea from the first quiz which we had done. This had similar kind of structure. The quiz has similar kind of structure. Okay, so this is what entailment means. Now, how will we use entailment? The idea of entailment. This is an algorithm which is known as model checking, which will help you come to a logical inference or logical conclusion. Okay, so how does model checking work? It is a method to verify whether a given model satisfies a knowledge base or not. Okay, so just we'll move on to maybe illustration. It is okay. So suppose, so with this illustration it will become easier, then I can go back and talk about what was it about. Okay, so you see, this is an illustration. It says that I have P, Q and R, three statements about my world. So P says that I have finished my homework. Q says that it is raining, and R says that I'll go to a movie. Okay, so P is what? P is this: I have finished my homework. Q is what? Q is it is raining, and R is I will go for a movie. Okay, so these are the statements I have, propositional statements I have. The knowledge base tells me that I have finished my homework. So P is true, and I say it is not raining. So I say not Q is true. So what is true? P is true and not Q is true. I have these two informations. I also have Okay, so okay, sorry, I am saying here. So if so, this says I have finished my homework, so which is P. It says it is not running, so it is Q. I have one more information. It says that if I have finished my homework and it is not raining, then which is implication, then I will go for a movie. So I have these three informations. I'll repeat again because I did not do in the order which it is written here. So what it says in the current knowledge base I have, if I have finished my homework and it is not raining, then I will go for a movie. So this is true because I have finished my homework. So P is true. It is not raining. It means not Q is true. And I have a and. So I have written and. Okay. If this and conjunction is true, then I will go for a movie. So R is true. Okay. So this is one knowledge. This is one knowledge I have. Another knowledge which I have is I have finished my homework. So P is true. And another information which I have is it is not raining. So I have not Q. Okay, so these three informations I have, and I want to come to a conclusion. Did I go to the movie or not? Okay, so this is the conclusion or I have. So you see how model checking works. What we do is we list down the propositional statements we have. So P, Q, and R, and list down all the models I have. So this is model 1, this is model 2, this is model 3, and so on. Model 8. Okay, you see false, 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 true. I have listed down all possible combinations of P, Q, and R. I have listed down all possible combinations of P, Q, and R. Now I have to reason out in which world my knowledge base is true. So I have to check which world my knowledge base is true. So in my knowledge base, I know P is true. So P is true in all these four worlds. So my knowledge base is false over here, my knowledge base is false over here, here, and here. Okay. My knowledge base also says that Q is not true. So when Q is not true, so Q is not true. So in this world and in this world, right? These worlds will not satisfy my knowledge base. These four worlds where I have circled, these four worlds will not satisfy my knowledge base because I am saying not Q is true. So when I say not Q is true, the knowledge base I have is Q is false. Therefore, these four truths are not possible. So this world is also not possible. This world is also not possible. I have these two worlds which is possible by the two information I have. These two information. I have one more information which is this, which says if P is true and Q is false, then R is true. This is one more information I have. So P is true over here and P is true over here. Q is false over here. Q is false over here. So this is true. This is Q is false. I have done it. In that case, R must be true. So when is R true? R is true over here. So this is the world where my knowledge base is true. This is the world where my knowledge base is not true. So in all possible worlds, there is only one world where my knowledge base is true. Okay. Now I am checking my query. Whenever my knowledge base is true, then my query should be true. Okay. So this is how entailments works, right? So what I'm saying is I have a knowledge base alpha. In all possible worlds where my knowledge base is true, alpha is true, the query which I have, the question which I have, beta must be true. So you see what is my query? My query over here is R. So I have to check whenever my wherever my knowledge base is true, R must be true. So my knowledge base is true only for this world and my query is what? My query is R. So you see the R value is true. Therefore, the knowledge base entails the query. And we can conclude that the query is true. So this is the algorithm. You see, this is a very simple logic. If you read this statement, you can just convey, yeah, it went to the movie. Okay. But how will a computer do it? This is how a computer will do it. It will list down all possible worlds. It will check in which of the world my knowledge base is true. That means which of the worlds satisfied my knowledge base. In all such worlds, if my query is true, Therefore, I can come to the conclusion that the query will be true. This is how the AI agent will solve this logical problem. If you want to take a minute, read or ask me questions, you can do that. I'll just reiterate again. It might not be clear maybe. If you have questions, you can just ask me, okay? So I have my knowledge base. So the knowledge base I have is P is true, not Q is true. And one more thing is I have is P and not Q implies R, okay? So this is my knowledge base. So I have to check in which worlds my knowledge base is true. So first P has to be true. So P is true here, 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 and here. Therefore, in these 4 worlds, my knowledge base cannot be true. So I can say this is false, this is false, this is false, and this is false. Now not Q is true means Q is false. So this is here false, this is here false, this is here false, this is here false. So in these worlds, my knowledge base can be true. So where my knowledge base is false, these two my knowledge base is false, and these two my knowledge base is false, right? So these two are my potential worlds where these two statements are true. I have one more statement in my knowledge base, which implies that if P is true and Q is false, R is true. So this is only the world which satisfies this condition. So this becomes false. My knowledge base becomes true in this world only in this world. So what I have to check, whenever my knowledge base is true, I have to check the query in this world has to be true. Okay. In this example, I have only one true. It can happen that you have multiple truth knowledge base in different models, right? In all those models, the query has to be true. Then the AI agent can come to the conclusion that with the knowledge base I have, the query is true. Is it clear?
Yes, sir.
Any doubt? Okay. So I'll just see what did I miss. So yeah, so I talked about knowledge checking. So you can just read whatever I have told you is written here. Okay, yeah, I have whatever I've told you is what it is written here. You can just go back and read. If you don't understand, you can ask me in the next class. Okay. Okay, so what do I have here? Definition of propositions. Okay, so what I'm doing is I'm just explaining the solution steps over here again. And now I will tell you how to write a algorithm for this problem. So you see, you have to specify the different symbols you are using. So you have to specify to the computer that I have a symbol P, and the meaning you can understand, the computer will not understand. But when the computer says P is true, you can understand that I have finished my homework. When the computer says that P is not true, then you can understand that I have not finished my homework. So you have to specify to the computer, I have 3 statements P, Q, and R. Okay. Then you have to give to the computer the knowledge base. The knowledge base is, this is the first knowledge base, this is the second knowledge base, and this is the third knowledge base. The 3 things you have to give to the computer. So what you have given a knowledge base to the computer. You have to give the query. What are you asking the computer? So over here I'm asking whether R is true or not. Okay, so this is the question I'm asking the computer. And the S is the set of all propositions contained within. So I'm saying this set is S. Okay, so this is the first proposition, this is the second proposition, and this is the third proposition. Why I'm specifying S? Because I will use it in my algorithm. Okay, that is why I'm specifying S. So this is the model checking algorithm. What is the objective? Check if the query is entailed by a knowledge base P. So what does it mean? It says knowledge base should entail Q. Okay, so whenever my knowledge base is true, Q has to be true. If that is the case, then I can come to the conclusion that my query is true. What is the algorithm? Initialize the set of all possible models. So you have the list of symbols, develop all possible models you can develop. And okay, so using the truth assignment. Now for each of the model, check if the knowledge base is true or not. And whenever the knowledge base becomes true, you have to check the query is true or not. If the query is true, mark the model as valid. If for all models, so if all models verify that Q is true, then you can conclude the knowledge base entails Q. But if there exists at least one world where Q is false, then you can conclude the knowledge base does not entail Q. Okay. So this is the algorithm which we are using. This is very simple. What are we doing is we are developing all the possible models, checking when the knowledge base is true. Whenever the knowledge base is true, I have to check my query is true. If that is the case for all possible models, then I'll say that knowledge base entails Q. If there exists one world where the query is not true, but my knowledge base is true, then I will conclude my knowledge base is not sufficient to entail Q. I may need more information. Okay. So this is the model checking algorithm. Okay, so this is one part of today's lecture. Any questions? Now you might think that I am enumerating all possible models. So when your propositional symbols becomes large, then the number of models which you have will become huge. And in such cases, it will become exponential actually. And in such cases, the algorithm which we are saying that model checking algorithm, it will not be an efficient algorithm. It is a correct algorithm. It will give you the solution if the algorithm terminates, but it is not an efficient algorithm. It will take a lot of time because we are enumerating all possible worlds. So we have to find another better way to solve the same problem. So we are moving on to a better way to solve the same problem. Okay. Any questions? All right. So what is a knowledge-based agent? So a knowledge-based agent utilizes the knowledge base to reason out and make informed decisions about the environment. So just like an AI agent. So AI agent is a knowledge-based agent. So what does it do? It takes information and reason out and make decisions about the environment. It also does is whenever you give him new information, it will update its knowledge base and then again use the updated knowledge base to make logical inference. If it can come to a conclusion for a query, then it will say, yes, I have come to a conclusion. If not, then it will say that I have not been able to come to a conclusion with the new information which you have provided. Okay. So these are the steps for reason out, perception, updating, and inference. So if you give a knowledge base, it will first infer. If it couldn't come to a conclusion, you have to give more information, and so on and so forth. So for example, if there is a robotic vacuum cleaner in your home, it detects some obstacles and then it updates its knowledge base, and it will know that the next time when it visits to clean some area, it will know that there is some obstacle and it will not go in that direction. Okay. So this is one example. Now we'll talk about knowledge engineering. So knowledge engineering is the process of designing and building systems that use the knowledge for reasoning. It involves determining what knowledge should be represented and how should it be constructed. Okay, so this is how we will represent knowledge and how we will reason out. That is what knowledge engineering is all about. So what is the process involved? You identify the domain and relevant knowledge to represent. So this is talking about a higher level. So when you have some problem, you have to think about which domain it belongs to. Now you have to think about how will you represent knowledge and what are the informations you have to represent as propositional statements, and so on and so forth. Then you have to choose the representation scheme. So you can have, okay, what here it is talking about is we had only talked about propositional logic, right? There are different ways to represent facts about the world. So there are frames, ontologies. We will not go into all those. Okay. We will talk about logic, and there are two kinds of logics we will talk about. One is propositional logic, which we saw earlier, and there is another form of logic which is first order logic. There are other higher order logics as well, second order logic, and so on and so forth. But as you go higher above, the computational time to solve the problem becomes larger, but you can convey more information using higher order logic. Okay. We will talk about this idea when we go to first order logic. Okay, so this is what knowledge engineering is. Now we will see some examples, and this will give you direction of another way to solve the same problem. Okay, so we have a weather prediction system, and these are the facts about the worlds which we have. P says it is cloudy, Q says the temperature is below 0, R says it will snow, and S says it will rain. Okay, so these are the propositional symbols I have, and this is the knowledge base I have. P and Q implies R. And what does it mean? If it is cloudy and, so P is cloudy. So if it is cloudy and the temperature is below 0 or below freezing, then it will snow. So this is my first statement I have, the first knowledge I have. Another knowledge I have is if it is cloudy and above freezing, then it will rain. Okay, so these are the two ideas I have in my knowledge base. Okay, so these are the knowledge I have in my knowledge base. So I have told you these are the knowledge we have. So suppose the meteorological department observes that it is cloudy. Okay, so this was my initial knowledge base. Then I'll give it more knowledge. Okay, so what is the knowledge I gave him? I gave him that it is cloudy and the temperature is below 0 degree. Then what will we deduce? You see, what are we saying? We are saying that it is cloudy. So P is true. Okay, it is cloudy. And I'm saying the temperature is below 0 degree. So when it is cloudy and the temperature is below degree, then I can conclude that it will rain. So I can conclude R is true. Okay. Now I'll update this knowledge. A later observation indicate that the temperature rose above 0 degree centigrade. Now what I say that Q is not true, not Q is true. Then I'll update my knowledge base as not Q. It is not below freezing. Now what will be my prediction? You see, I'm saying it is cloudy, but the temperature is not below freezing. It is above freezing. Now my conclusion will be it will rain. So this is how we update our knowledge base. So over here in this example, I'm just showing you how are we updating our knowledge base. Okay, that is it. So I have my initial knowledge. So this is the initial knowledge and I give it more information. And with that information, I can reason out to a conclusion. Okay, I can infer more information about my world. Okay, so through the continuous observation and updating of knowledge base, it can improve its accuracy. Okay, so this is how inference works. So you have a knowledge base, observe, then you come to a conclusion and continuously update and observe, update and observe, and so on and so forth. Very simple algorithm. Now we will come to inference rules. So you see in the previous problem when we were solving it using model checking, there also we were doing inference. We had some knowledge and we had a query and we are coming to a conclusion whether the query is true or not. So with the knowledge base, I am inferring whether my query is true or false. Over here also we will use different kinds of ideas to do inference. Okay, so what are inference rules? Model checking can be resource intensive. So I told you you have to enumerate all possible worlds, so which requires exhaustive enumeration of all possible worlds. So it is not an efficient algorithm. Okay, so yeah, so this is here. So what is an inference? Inference is an act of deriving new conclusion based on the established facts we have using logical principles. So in the previous algorithm, you see, we were not making inferences with the worlds with the knowledge we have. We had the knowledge. We were checking that when the knowledge base is true, the query must be true. But over here, I am saying I have existing information. Use those information to come to some conclusion and update your information about the world. So this is what inference is. You have information, come to a new conclusion, establish new fact about the world. This will help you know your world better. Okay. Yeah. So I have some rules which is known as, so I'll list down some rules. First is modus ponens. What does it mean? It means that, so suppose there are two statements. First is P implies it is sunny and Q implies Alice is outside. So when I say P implies Q, so when I say this is my knowledge base and I also have P is, so it is sunny. So I have my knowledge base P implies Q and P, then I can logically conclude that Q is true, right? So I have my knowledge base as P implies Q, and another thing I have in my knowledge base is that P is true. So therefore I can come to a conclusion which is Q is true. Okay, so in logical inference, how do we represent it in logical inferences? You write the knowledge base in the fractional form. So write in the numerator the knowledge base which you have. So it is P implies Q and P. So these are the two things we have in the knowledge base. Below you write the conclusion you are deriving from the knowledge base. So from this knowledge base I can derive that Q is true. Okay, so this is what is modus ponens. The second is modus tollens. It says that I have two statements R and S. It says R is snowing and S means the road is slippery. And I have in my knowledge base R implies S, and in the knowledge base I have not S. Okay, so this is what I have in my knowledge base. What can I conclude? I can conclude not R. So you see, you have to think about it. So in the truth table, I'll just help you understand this with a truth table. So I'll go back maybe. Okay, so where is it? Yes, so I have in this truth table, if you check here, so what I had R implies S and not S. So for this example, it will become P implies Q and not Q. Okay, so you see, when this statement is true, this is true, this is true, and this is true. Okay, these are the three cases when this statement will be true. And when not Q will be true, when Q is false. So in this case it will be true, and in this case it will be true. So you see, both are happening only in this case. Both are happening only in this case. And what is the value of P? Then P is false. Therefore I can conclude that not P is true. Okay, so this is what their idea was. So when you have R implies S and not S, then you can conclude not R. Okay, so this is one more. So what are we doing? We are giving rules to the computer. We are saying that if you have this in your knowledge base and this in your knowledge base, you can conclude this from your you can infer this from your knowledge base. Okay, next is AND elimination. So if I say, so this is very simple, by the way. If I say T and U, so you can conclude T is also true and U is also true. So in your knowledge base, so you have to write like this. In your knowledge base, if you have T and U to be true, then you can conclude T is true, and you can also conclude U is true. Okay, so these two conclusions you can come. Obviously, if I know this to be true, and says when both are true, then this statement is true. So therefore T is true and U is true. So we can conclude T is also true, U is also true. This is very trivial, by the way. Is it clear? Okay. So the next is OR introduction. So what does it mean? So if I have a query, which is not query, sorry, propositional statement as V and W, I can just introduce myself that either V is true or W is true or both are true. Okay. So this is OR introduction. The next is double negation. It says that if you have a statement Y, so this meaning it is not necessary. You have to just understand the idea. So it says that if you have not Y, then not Y will just mean Y. So it is not like this. So you have to write like this. So if you have not Y, then you can deduce Y. So it means that when not Y is true, then Y is true. Double negation. Is it clear? So if Y was true, then double negation will also be true. Or in the other hand, if you double negation Y is true, then Y is also true. The next is implication. So if Z implies A, so this is important, by the way. If Z implies A, then I can write not Z or A. Okay, and this you will be able to understand by the example. So I'm saying it is raining, and I'm saying Bob is at home. So what is mean? If it rains, then Bob is at home. Okay, so this implication Z implies A. This is what it means. If it rains, then Bob is at home. What does this mean? Not Z or A. This means it is not raining, or Bob is at home. Okay, now reason out. If it rains, then Bob is at home. So when rain is true, then you can conclude B is true, or A is true over here, right? A is true, right? So you see, OR statement has, it can happen that both are true. So this case, you are okay. You can have Z as false and A as true. So can this happen? If this is false, this can be true. Yes, implication says that when this is false, you have no idea about this. So this case works for implication. So you see, this is false and this is true. Then this becomes same as this. You can have another world where this is false and this is false. So implication will work. So if this is false, then you have no idea about this. So this will also work. And you see, so okay, this is not raining. So not raining will become true or false. So this will also work. So this was not raining, huh? And another world which I have is F is true, but A is false. This will not work for implication. Implication doesn't work for this case. So implication is true for this case, and this case only. Okay. So it just says you can draw a truth table and you can just see. So I'll just help you again maybe with the truth table. Okay. Then it will be more clear. So I have Z A, I have Z implies A, and I have not Z or A. Okay. So this is 1 0 0 1 1 1 and 0 0. So implication is false only when this is true and this is false. Okay, otherwise it is true. When this is true and this is false, then only implication is false. Now we have to say not Z or A. So what is not Z? Not Z is 0 and A is 0. So this will be 0. Not Z becomes 1 and this becomes 1. So this is 1. Not Z becomes 0 and this becomes 1. So this becomes 1. Not Z becomes 1, A becomes 0. So this becomes 1. So you see, whenever, so all these are happening the same. So therefore what this AI agent can conclude, it can conclude that if I have A implies Z implies A, I can change it to not Z or A. Okay, so this is the idea. Implication elimination. So we are eliminating implication. The next idea is biconditional elimination. So it says that if you have like this, B, if and only if C, then you can write two implications. You can write this as, so not like this and not right. It's like this. B implies C and C implies B. So you can negate, so you can eliminate biconditional by two implications. Is it all right? So what are we doing? We are simplifying our knowledge, right? So I have some knowledge. I am changing biconditionals to implications, implications to and or, and then I can reason out about the world. We are simplifying the knowledge which we have, right? Is it clear or is it becoming confusing?
Yeah, clear.
Okay. So there is De Morgan's law. So this is might be you have read this about in mathematics. It says that if you have a negation outside, so suppose it is or, so this can be written as not D and not E. Okay, so just move the negation inside and change and to or. So this is one De Morgan's law. There is another De Morgan's law. It says that not D or E, this will become not D and, so it is not, so it is or, it will become and not E. Okay, so these are the two De Morgan's law. So one is for conjunction, another is for disjunction. So this and is conjunction, or is disjunction. So this becomes this and this becomes this. Just move the not inside and change conjunction to disjunction and disjunction to conjunction. Okay, these are De Morgan's law. Distributive property. So this is also very easy to understand. So if you have a condition like this, F and G or H, this will become, so you shouldn't write like this, by the way, this will become F and G or F and H. And if you're thinking why this is happening, you can just take this example and then you will be able to understand that this happens. What it is doing is it is moving and inside. So F and G or F and H. Okay. And one more distributive property is there. So if you have F or G and H, then this will become F or G and F or H. Okay. So this is another distributive property. Now we will see how, so we have seen some rules to simplify our knowledge base. Now we will see how will we make inference. So understanding inference rules. Inference rules offer systematic method for deriving conclusions from premise. Premise is what? Whatever you are given. From that premise, you're deriving some conclusion. So whatever we have learned till now, we will use those to derive new conclusions. These rules helps extract knowledge, new knowledge based on the established logical relation. So whatever you have in your knowledge base, you can use that and use this rules to make, develop or extract new information from the knowledge base. Okay. Before that, you can formulate this as a search problem. How? So you see, by the way, there is a better method than solving this as a search problem, but we are talking about search problem because we had discussed search problem earlier, and I wanted to show you how versatile search problems are. So what you can think is you have a current knowledge base and you can think about as the initial solution or initial, not solution, initial state. What actions you have, the inference rules you have are the actions you have. So you can convert the statements you have inside your knowledge base into different forms. So those are actions you can take from the current state, right? What is the transition model? So from the current state, taking an action, what will be your new knowledge base? That is the transition model. What is the goal test? So when your knowledge base has the query, then you can say you have reached the goal. And path cost can be you are trying to minimize the steps you are taking to reach the goal. So this is not how will we solve this inference problems, but I wanted to give this idea to you that you can use the idea of search problems to make logical inferences. Okay. The, the most powerful idea for solving this kind of inference problems is resolution. We will take 5 minutes break and then come back and talk about resolution. Okay. So we'll meet at 7:10. If you have questions, you can ask me now. So I will ask you one question. Whatever I am explaining, is it clear or is it going above your head? So I should know, otherwise I'll not be able to modify my teaching methods or improve my teaching methods.
Yes, sir.
Okay. Okay, so we'll meet at 7 or 10. 7:10. Okay, so we will talk about resolutions. So before going to resolutions, we will talk about what are clauses. Okay, let me see. I have given some definitions of clauses as well. Okay, so what is a clause? A clause is a disjunction of literals. So what are literals? Over here I will say, so I have written here, literal is the propositional statements which we have. It can either be that propositional statement or negation of the propositional statement. So I can have either P or not P. So these are known as literals. What is a clause? Clause is a disjunction of literals. So P or Q, and literal can have multiple propositional symbols also. So for example, I can have like this. So P or, so I can have P, A or B or C. So this is one clause. So clause 1. D or not A. This is clause 2. F or G. This is clause 3. Okay. So what is a clause? Clause is a disjunction of literals. It can either be uh, in the form which is it, or it can have a negation form. Okay. So this is what a clause is. So what is resolution? Resolution is a robust inference rule which utilizes conclusion, which derives conclusion from the disjunction of literals. So what it means is you can have clauses and it uses this or idea of or to come to conclusions. So I'll give you one example. So if I have P or Q and somewhere later time point I realize that not P is true, therefore P is false, and I can conclude that Q must be true. Okay, so if P and Q holds, and I know from my knowledge base or in later time point there comes a knowledge to me that not P is also true, then I can conclude that Q must be true. So why this is important? You see, we have learned a lot of rules to convert one statement to the other. So what we'll do is we'll try to convert those statements in the form of disjunction, in the form of not, not, in the form of or. And whenever I have an information which says, so whenever I have like this P and not P, then I can just cancel out both of them. So I can just say we are cancelling out P and not P, and therefore Q will be true. So this is the idea of resolution. We are using the inference rules. So these rules which we have discussed are known as inference rules. And we use that inference rules to derive conclusion from disjunction of clauses. Okay. So I've given one example. It says that either the cat is on the roof or the dog is in the yard. And at a later time point, I know that the cat is not on the roof, then I can conclude the dog is in the yard. Okay. So this is the definition of resolution. So resolution is a both sound and complete uh, method to solve this. So these are terminologies, these are technical terminologies. What is sound and what is complete? So sound means it only produces valid conclusions. So you cannot reach an invalid conclusion. And what is complete? In all the possible cases where you will have, where you could come to the conclusion that your premise is true, it will come to that. It means that it will be possible to list down all possible cases, and whenever your knowledge base is true, you can conclude your this query is true. So it is complete in all possible cases. It is complete. Okay. So knowledge and complementary. So you see, we talked about this disjunction. So we have to talk about how resolution is using this disjunction and the idea of complementary literal. So what is complementary literal? So if I have P, not P is the complementary literal. Okay. So this is what complementary literal means. Okay. So for instance, we can represent complementary literal as P and not P. So resolution can be extended with this idea. So suppose I have a statement C or D, and I have a statement not C or P. So what I can do is I can use the idea of resolution, and I can cancel out C and not C. What my new just a minute. Okay. So this is not what this example was. So this example is, it says, so it says that C or D. So it says that the cat is on the roof or dog is in the yard. So this is one statement I have about my world. That either the cat is on the roof or the dog is in the yard. Another statement I have is the cat is not on the roof, and P means the pig is sleeping. So if both of them are true, then I can conclude that this and this cannot happen together, right? C and not C cannot happen together. So I can conclude that either the dog is on the yard or pig is sleeping. So just reason it out. Take a minute and reason it out. You see, I have C or D. Okay. So what can happen over here? C can either be true or C can be false. In that case, when C is true, then D can be true or false. But when C is true, D has to be true, right? So this is the all possible cases. Not C or P. So what happen is, so you can have C as true. So when C is true, then this becomes false, and this will have to be true. When C is false, then this becomes true. Then this can either take true or false value, right? Now you see, when C is true for this case, we have for D true or false. And in this case, we have true. And when C is false, in this case I have true, and in this case I have true or false. Therefore, this case matches with this case, and this case matches with this case. So you can just write D or P. So you see, D or P happens when D is true, then P can either be true or false, but when D is false, then P has to be true. So this is, and not using this idea, you can use the idea of English to come to this conclusion as well. So whatever I have written over here, you take a minute, read, and if you have questions, you ask me, because this is important to understand. So what does the first statement say? The cat is in the roof or the dog is in the yard. The second statement say the cat is not in the roof or pig is sleeping. So we can deduce from this that either the dog is in the yard, because in that case the cat is not on the roof. Therefore, the pig can be sleeping or cannot be sleeping. But if the dog is not in the yard, then the cat must be in the roof. And when the cat is in the roof, then this is false, then the pig must be sleeping. So either when this is true, then it doesn't matter what the value of this is. But when this is false, this must be true. What I mean is, when this is false, this must be true. But when this is true, it can take either true or false. And the reverse case is also true. When this is false, then this must be true. Then this must be true. And when this is true, then it either take true or false. Okay. So this is the idea. So this is a way resolution works. You see, we are removing C altogether. We are left with D and P. Are you able to understand? Are you able to understand? So I'll take another minute to explain. You see, what does it say? The dog is in the yard. So when this becomes false, this becomes false, when the dog is not in the yard, what will happen? When this is false, then cat must be in the roof, right? Cat must be in the roof. And when cat is in the roof, then not cat will become false. And from this statement, P has to be true, right? Because this is false, then P has to be true. Therefore, you see, this is false and this is true. This becomes false and this becomes true. OR is working, right? And you can reason it out on the other way also. You see, suppose P is false, that P is not sleeping. When P is not sleeping, then not C will become true, right? Because we have this statement. Now when not C is true, then C is false. Now when C is false, then D must be true. Therefore you see one is false and the other is true. Okay, so this is true and this is false. And there is one more case also when both are true. This can also work if you reason it out in this way also, then both can also become true. Is it clear now? Okay, thank you. Okay, let it be. Okay, so we have talked about disjunction. We also have conjunction. So conjunction means and. So when I say conjunction, it means and. When I say disjunction, it means or. Okay. Now we will talk about what is conjunctive normal form. So what is conjunctive normal form? Conjunctive normal form is when we have clauses and we have multiple clauses and all those clauses have and in between. So what is a clause? Clause can only have or. Okay, so clause can only have or. And when this clause are connected using an and for all the statements you have, then it becomes conjunctive normal form. Okay, so conjunctive normal form is a special form where you have clauses and the clauses are connected with and. Okay, so this is what a conjunctive normal form is. Okay. So this is what it is, and this is one example. Why are we talking about conjunctive normal form? Because there are many inference algorithms which use conjunctive normal form to come to this inference, to solve inference problems. Okay, so that is why we are talking about conjunctive normal form. And now if you think about it, you know a lot of inference rules. So you can have implications, bidirectionals, and so on and so forth. You can convert any of those to conjunctive normal form. I have taken examples to show you conversion to conjunctive normal form. So any statement you can convert to conjunctive normal form, and we'll see one example. Okay, so elimination, implication. So you have implication. So we talked about implication. P implies Q. We know that there is an inference rules that convert implication to or. So this will become not P or Q. So you see, you have a clause. So this is a clause, right? Right? Again, negation. So suppose you have not A and B. So what you can do is you can just convert it to A, not A or not B. So we are converting what we have into clauses. What is a clause? A clause is multiple literals connected with or. Okay. Double negation. So if you have two negation, you can just remove the negation. It doesn't apply here. Distributive property you can use. So I have written over here. So you can use the distributive property to convert and to or. So some examples. So suppose you have this formula which says that not P and Q or R. So what you can do is you can first take this distributive property and you can put it inside. Before that you can just take the negation inside. So when you take the negation inside, what it becomes? It becomes P, sorry, it becomes not P. It becomes not P or not Q, right? So have I written it properly? Okay, so I guess I have not written it properly. Nevertheless, you can just, so it will not become this. Okay, so what it will become is not P or not Q or R. So this is what it will become. So this will become this. How will this come? So suppose you had not P or Q or R, then you can take De Morgan's law. So it will become not P and not Q or R. Now this will become not P or R and not Q or R. Okay, so this is the, if you have this, then it will become this. If you have this, then it will become this. So the overall idea is you can convert any statement to clauses and then to conjunctive normal form. Okay, so So this is a conjunctive normal form. You have two clause, clause 1 and clause 2 with a conjunction. So I had made this in a hurry. That's why I have given over here and it should have been or. The idea is clear, right? Now you may ask, if I have a bidirectional, what should I do? So you see, so these are some of the steps of converting any propositional statement to a conjunctive normal form. If you have a bidirectional, you can convert the bidirectional to two implications. So if you have alpha bidirectional beta, then it will be converted to alpha implication beta and beta implication alpha. Elimination. So we have seen that implication you can eliminate. You can make it as not alpha or beta. You can have used De Morgan's law. You can just do many more transformations and so forth and so on. So the ultimate conclusion is you can convert any statement to conjunctive normal form. So this is one example I have given. Suppose I have X. So you can take a minute and convert this into conjunctive normal form. So I have given the steps, but I'll just write over here. So I have X or Y implies Z. So you can just talk to me maybe. How will you convert it into conjunctive normal form? X or Y implies Z. First, what we have to do? We can remove the elimination, right? So what you can do is not X or Y or Z, right? So this is how you will do. So this will be converted to this, not X or Y or Z. Now you can take this not inside using the De Morgan's law. So it will become not X and not Y. And now you can take this or inside. So it will become not X or Z and not Y or Z. This is in the conjunctive normal form. Are you guys with me, or am I just speaking which you are not able to understand? Okay. Now we'll come to how will we use this conjunctive normal form and perform resolutions. Okay. So once you have the expression in the conjunctive normal form, you can apply inference algorithms. How you will do it? You will do factorization. So if you have this and this, okay. So you see this is in the conjunctive normal form. This is clause 1 and clause 2. So what you can infer is you can just infer. So how will you infer over here? You see, just a minute. What I have done over here is, okay. So what I'm doing is M or N or O and not M or P or O. So you see, you can just remove M and not M. So we have done this over here. So if you go over here, we saw that we can remove C and not C, right? So we can remove it. When you do that, then it will become, so what it will become, M and this not M will be removed and it will become, so what will this become? You will have N or O and this will become P or O, right? So this and this. Now again, if you go back, you will see, so this is over here you have and. Now I guess I have done some error. This must have been not O. So if this was not O, then it will become N. So if this was not O, then you can just use resolution and then remove O as well. So then it will become N or P. So to infer this, there must have been not O as well. So what are we doing? The idea is just we're cancelling out M and not M, P and not P, and then we are reasoning out. So if you have a very long statement which has multiple propositional statement with multiple logical connectives, then just cancel out the um, m and not m cases, and then you will come to a conclusion. When the resolution yields empty, so suppose this was, so I have one example, right? I have an example, right? So this is the example. So I have x or y and not y or z and not z, right? And what I have to do is I have to simplify this. So for the time being, just simplify this. So what it will happen is this z and not z will be cancelled out. Okay, this z and this z will be cancelled out. So we'll have x or y and not y. Okay, because we are removing these two. Now not y and y will be removed, then we will be left out with x only. Okay, so this is what will be left out with. So this is how we are simplifying our statements which we have. Now we'll have to think how will we make a logical inference. So this is how we are simplifying. Now we'll talk about how will we make logical inference. So you see, we had the idea of entailment. It says that I have a knowledge base. If it entails alpha, so whenever the knowledge base is true, alpha is true. So we'll prove this using contradiction. I'll say I have a knowledge base and I know that not alpha is true. So I'm contradicting. I'm saying suppose alpha is not true and I add it in the knowledge base. If this yields a contradiction, then what it means that the assumption which I had made that alpha is not true is false, right? So what I had assumed that not alpha is true. Let me assume that not alpha is true and I'll add it in the knowledge base. If this gives me a contradiction, then we will say that this KB entails alpha. My knowledge base entails alpha. So this is the idea of proof by contradiction. So I have a knowledge base. I will add one information. What is the information? I will say that alpha is not true. I will do resolution, and at the end, if I come to a contradiction, then I'll say that whatever I had assumed alpha not to be true was wrong. Therefore, alpha is true. Therefore, whenever my knowledge base is true, alpha becomes true and alpha entails, knowledge base entails alpha. Okay, so this is the steps. I'll just show you one example. So over here, I'm saying this is my knowledge base and I have to, the query is X. So with this knowledge base, is X true? That is my query. So what I do is with this knowledge base, I will assume that suppose X is not true. So what is my query? My query is X. I will assume that query is not true. So this is my knowledge base, X or Y and not Y or Z and not Z. I will say with this knowledge base add one more thing, which is X is not true. X is not true. Now what I will do is I will do resolution. I will remove Z and not Z. Then I'll remove Y and not Y, and I'll remove X and not X. At the end, I'm remaining with nothing. So this is a contradiction. When everything cancels out, then I have an empty set, which indicates a contradiction, and I can say, no, X is actually true. So what I assumed that X is not true is wrong. And therefore, my knowledge base entails X. So this is the algorithm. So what is the algorithm? Here are the steps of the algorithm. You have a knowledge base. You take this as your new knowledge base. What is the new knowledge base? You have knowledge base and you say and not alpha. Now you convert everything into the conjunctive normal form and then do resolution. After resolution, if you come to a contradiction, then you can say that my assumption was wrong and alpha is true. Therefore, this knowledge base entails alpha. If so, this is one case when there is a contradiction. If there is not a contradiction, then you can say I don't have any information and I will not be able to comment on alpha. So what is happening is this is your knowledge base and suppose this is your alpha. In such case, there will be no contradiction. And what you will say is I have no, not complete information. I cannot conclude about alpha anything. If you have a case like this, then there will be a contradiction and you will conclude that alpha is true. Okay, so in this case, you will not have a contradiction and you will conclude I don't have a lot of information about alpha and I'll not able to conclude anything about alpha. So this is the algorithm. Okay, so this is how this idea of resolution works. Okay, so we have done a lot of things on propositional logic. If you have not understood, you can ask me now, because we have talked about two ways to solve such kind of problems, and it might become a lot to take in one session. So how are we solving this problem? First, we had talked about model checking. So what you do is you have a knowledge base, you find all possible models where your knowledge base is true, and you check whether your query is true or not. Then we concluded that this kind of approach is not feasible for large problems. It will become computationally very expensive to solve your problem using this approach. Then we thought about using some idea of coming to a conclusion with your knowledge base, inferring more information about your knowledge base. We talked about some inference rules which we can use to get more information about the world using my knowledge base. And then we use the idea of resolution. What does it mean? It means that if you have a conjunctive normal form, then you can remove two literals, one and the other, which is the negation of that literal. So if you have x, you can remove x and not x together, right? So that is what we are doing over here. We use the idea of resolution. Now, how will we check entailment? We are saying you have a knowledge base. What you add to the knowledge base is the query is not true. So you are adding it to the knowledge base. If you face a contradiction, then whatever you have assumed is false. Therefore, the knowledge base entails X. Okay, so this is how we are using our knowledge base to come to a conclusion about the query. In the previous algorithm, we were not using our knowledge base to come to a conclusion. We were checking in which worlds our knowledge base is true, and in those worlds we were checking whether the query is true or not. Over here we are taking a different approach. We are just remaining in our knowledge base, we are modifying our knowledge, and then we are saying whether this query is true or not. If I can come to a conclusion about the query, then do it. Otherwise you say I don't have a complete information. So this is the idea of propositional logic and solution approaches to propositional logic. Any questions, doubts, concerns, comments? If you're not able to understand, you can say that also, okay, I'm not able to understand. Okay. So we had talked about propositional logics. Now we'll talk about first order logic. So this first order logic is an extension of propositional logic. So whatever you had learned in propositional logic will hold true for first order logic, but we'll introduce some more quantifiers and variables. So what are the quantifiers where, so you see, we didn't have this kind of terms in propositional logic. So propositional logic, whatever statement we had, it can only take true and false value. So suppose I have a problem like this. All the students in the class take mathematics. So this statement I have, all students take mathematics. Okay. Now to make a propositional statement, what you have to do is you have to list down. You have to say student A takes maths, whether it is true or not. Student B takes maths, and so on and so forth. So if there are 1,000 students, you have to make 1,000 such statements. Then only you will be able to say whether this is true or false, whether this is true or false. Okay, so in such cases you have to make 1,000 variables for 1,000 students. And suppose there are two subjects, suppose there are maths and science. Now what you have to do is, for this you have made 1,000 variables or for 1000 statements. Again, for science, you have to make 1000 such statements. Students A takes science, student B takes science, and so on and so forth. Then you can say this is true or false. Then you can say this is true or false, right? So this is one issue with propositional logic. Because it can only evaluate true and false, you have to make multiple statements to give this idea of all student takes something, right? So this thing is simplified when we are using first order logic with new quantifiers. There are two new quantifiers. So in the previous propositional logic, we had logical conjunctions like and, or, not, implication, biconditionals. Over here, we are introducing two new quantifiers. This upside down A is actually for all, and this opposite E is actually there exist. All right, so we'll take some examples to solidify the idea of these two new quantifiers. What do I mean by for all, and what do I mean by there exist? All right, now there are few more changes. So we are talking about two new quantifiers, but there are few more changes. You see, when I'm talking about students and subjects, I am repeating students. You see, I'm repeating A over here, I'm repeating B over here. Why should I repeat? Why should I make multiple variables for the same? Over here, you see, for maths, I am repeating 1000 number of times. Over here, I am repeating science 1000 number of times. Why should I repeat? If I can make one variable for that, then it will be better, right? We shouldn't repeat. So this also is simplified using first order logic. So what are we doing is we have terms and formulas. What is terms? Terms over here in this example will be, one term will be student and one term will be mathematics or subject, you can say. So I'll say term will be student A, student B, and another will be mathematics and science. So over here, suppose I had 1000 students and 3 subjects. 1000 students and 3 subjects, you would have needed 3000 variables, right? With 1000 for mathematics, 1000 for science, and 1000 for the third subject. But in this case, you see, I had 1000 students and I need only 3 variables for this subject. Suppose Hindi is there, right? So I only need 1003 variables. In this case, I needed 3000 variables. So you see, we are removing some statements from my, so we are simplifying the problem, right? So suppose there were not 3 subjects, there were 30 subjects. So if there were 30 subjects, then what would happen? You would need 30,000 variables in that case. But over here, using the idea of first order logic, you would need 1000 plus 30, which is 1030 variables only, right? Any questions? Are you guys here? Okay.
Yes, sir.
Yes. Okay. Now you see, we can have formulas. Thank you. So we can have formulas as well. Like you see over here, we needed to connect students and subjects using this take. So we can define formulas. We can say take as a formula. It takes 2 inputs, a student name, suppose I say A, and a subject, say mathematics. Mathematics, right? So this formula can relate to different variables. It is relating student A with the subject maths, right? Before that, before the introduction of first order logic, we had to introduce multiple variables relating each student with each subject. Now what I'm doing is, this relation is taking the form of a formula. I'm saying if take A and mathematics is true, it means student A takes mathematics. All right. So these are the 3 components of first order logic. Terms, we have formulas, and we have new quantifiers. All right, so these are enriching your model, new consideration in your model, which will help you add more complex information in your model. Okay, so when I say like Alice comma ice cream, it means Alice likes ice cream. Okay, so what is the next idea? So you see, I told you that we have new quantifiers or not or sorry, for all, and there exist. So I have given some examples to solidify this idea. So what is the first problem? The first problem says is every student who studies passes the exam. So how are we writing it? So if you are familiar with mathematical notations, then it will be easier for you. Otherwise, just follow along with me. How to read this? You see, this student is a not student. This pass exam student. These are formulas. Okay, these are formulas. And this x is what? X is a variable for me. So over here, this student A, student B, these are in X. Okay, so these are the variables. So I'm saying for all students or for all X, this is X are what? These X are students. So whatever X I have, of all those X's, which are students, so I can have various other variables as well. Some can be professors, some can be teachers, some can be plumbers, and so on and so forth. But from those X's, if that X is a student and it studies, then these X's which are students and they are studying, then they will pass the test, pass the exam. So I'll explain once more. This X can contain multiple variables. It can have students, it can have professors, it can have plumbers, it can have businessmen, and so on and so forth. This statement says for all those X's which are students and these students are studying, then these students who are studying will pass the test or pass the exam. Okay, so this is the idea of, so you see such complex ideas, you are able to represent it and tell to the computer that this simple idea. Okay, so there can be multiple X's. You are saying for all those X's who are student and these students are studying, if these two together is true, then they will pass the exam. Those X's will pass the exam. Is it clear? Is it clear? Okay. Now this idea is for there exist. Okay. So this says there exist. So you have multiple X's. All right. But this is there exist at least one student, because I have here student. So there exist. So you have thousands and thousands of X's. X can take thousands and thousands of variable, but there exist at least one student which had studied and passed the test. So there exists a student who studied and passed the exam. Okay, so this is what there exist means. So there is at least one student which studied and passed the exam. This is what this there exist means. Is this idea clear? Right. And over here I have added both for all and there exist. So what is the idea? For every student, so for every student there exists a subject that they will study. So what does it mean? That if you are a student, so there may be multiple X's. For all the X's which are students, so you can have plumber, businessman, housewife, so on and so forth. For all the X's which are student, there exists a subject, and that subject the student has taken. So you see, we have two kinds of variables. We have X variable and Y variable. Okay, so they are saying that for all the X's you have which are students, there will be a Y. There will be a Y which is a subject. Okay, Y can take other things also. So Y can take subjects, exams, and so on and so forth. So for all the X's which are students, there will be a Y which is a subject, and this student has taken this subject. So there will be a subject which this student X has taken. So this is what this representation means. Any questions?
What does that imply indicate in the solution? Implying.
Implies. It means that if you have a student, then there will be some subject. So if student X is true, then the right hand side will also be true. So if this evaluates to true, then this will evaluate to true. So implication, which we were talking about in the propositional logic, that is over here. All right.
No, how to read this with that imply sign for all students? It is implied that there
No,
exists
you read in
at
English,
least
read
one
in.
subject that they will study.
So I'm saying when you read in English over here, when you are saying they exist, so it means that you are assuming that this is true, right? So when you say if X is a student, then this will happen. So you are assuming that there is a student which this student is true. So you think about it. When you are telling this statement, are you assuming this is true or not? Think about it.
Yeah. Yes.
Right, so that implication is coming over here. So you're saying for all those X's which are students, that means there is some student. For those students, the right hand side will be true. So if this student is true, then the right hand side is true, right?
Okay. Yeah. Means this condition says that there is at least one subject which a student studies.
Right.
Can there means can there be a case that there is a student, there are subjects, but he is not studying? Can
So,
it be a case?
so for every student, there exists a subject that they study. So there may be a subject which a student may not take. Yeah, there can be.
Yeah.
Right. So anything else?
No.
Okay. So conclusions. So we have learned various systems of. So you see, we speak in natural language, right? So computer doesn't understand this language. So we have to write ways to how to make computers understand. So these are ways to represent the knowledge and give it to a computer. So, and then the computer will use the idea of inferences. So we have not talked about inferences in first order logic because that becomes more and more complex. If you are interested in this part, you can read those sections also. But how will we solve problems with these ideas? So either you can use propositional logic, but in that case you will have multiple variables and you have to, that model will become very complex, or you can use first order logic. And what is the solution approach again? So there is inferences approaches to solve first order logic. We are not talking about the approaches used in first order logic to solve the problem. Okay. And this is how knowledge is represented in AI, and uh, AI comes to an inference. AI can conclude with the knowledge it has. These are the references I have used. I know today's class was a lot to take. You can ask me any questions anytime you want in the next class. Anything else? Okay, so some quick announcements. So first you have first thing is you have the deadline is Tuesday 12 p.m. So please submit your assignment before that time. The second is we will not have class this Tuesday. The third is I'm going home for 10-15 days. So I will be on low on internet speed. So I'll try to have good internet speed. If there is a problem in next class with internet speed, then I'll record lectures and upload. I hope there is no such issue. So yeah. And one more thing, during the Diwali week, I may skip one class. And if that is the case, then I'll take extra classes. Any doubt?
No, sir.
No.
Okay, so Jairaj, you had some question on this, right? The assignment.
DFF.
Okay, so if anybody doesn't have any more questions, you can leave the meeting now. Okay, so yeah, what was your question?
Shubham, to begin with, I hello.
Yes, you are audible.
Yeah, I understood the depth first search algorithm. No doubt, means conceptual wise, that's okay. Means start with 0 0, search for child cells, stack those child cells, again check for one, again check whether the child cell is one. If yes, stop there. If not, again check for the child cells, and so on, and just enlist all those cells in the visited, and finally check whether you have reached the goal point or not, and display. Correct?
Yes.
But I am unable, not unable, I tried a lot to optimize the algorithm so that I can write a best suitable pseudocode, but somehow messing it up.
Okay, so let us discuss. So what you have first is,
Means I I took input from user.
okay, so you have a maze which is of the
Yeah, I have a maze
2D list, right?
3 2, okay, 3 by 3 matrix.
Yes, yes, yeah. So it can have, yeah. Then,
then then I declared start point and end point, means 0 0 and 2 2.
okay,
Then I defined two variables like I and j, so as to indicate, as you wrote as 0 0, so as to indicate, means cell number 0 0, I use.
just 1 minute. I'll just end the recording first. Just a minute. Yes, tell me now.